right, hello and welcome everybody. My name is Laurel Glenn. I'm the project manager of safety. We appreciate you joining the webinar today that's on real-time risk prediction at signalized intersection using graph neural networking. You've all come into this meeting muted with your cameras disabled, but if you have any questions during the presentation, you can feel free to use the chat box, which is below in the dock of your Zoom window. You can also use a question answer option if you wish, and we will get to those at the moment or during the question and answer section, which will be at the end. If you would rather ask your question yourself, we highly encourage that. So all you have to do is raise your hand or send me a chat message, and I will unmute your mic for you to discuss as you will with our presenters. We encourage that conversation as long as you feel comfortable to do so. All right, so at this time, I would like to introduce the presenters today. Abhijit Sarkar is a senior research associate with the Division of Data and Analytics at the Virginia Tech Transportation Institute. At present, he leads the computer vision and machine learning team at VTTI. And his research mainly focuses in intersection of artificial intelligence and transportation research with an emphasis on computer vision. This includes safety and operations of automated driving systems, driver distraction and attention monitoring, intersection safety, unmanned aerial vehicles, multimodal sensor processing using naturalistic driving data, and AI application in driver health monitoring. He received his doctorate degree from the Department of Electrical and Computer Engineering here at Virginia Tech in 2017, with a focus in computer vision and remote health monitoring. Prior to that, he received his master's in electrical engineering from Indian Institute of Technology in Kharagpur, India, and his bachelor's degree in electrical engineering from Jadavpur, India. His research has been funded in multiple federal and state agencies, including NSF, FMCSA, NHTSA, FHWA, and CHRP, and of course, right here, the University Transportation Centers. We also have Akash Sonth, who is a recent master's graduate in computer engineering from Virginia Tech and was a graduate research assistant at VTTI here during his master's degree program. He's currently working as a data scientist in Aspen Technology in Bedford, Massachusetts. He received his BE degree from the Birya Institute of Technology and Science in Pilani, India in 2019, majoring in electrical and electronics engineering. His research interests lie in the intersection of computer vision, perception, and intelligent transportation. So at this time, I'm going to go and hand it off to you, Abhijit.
Okay, can you hear me?
We sure can.
Okay, so I will go ahead and share my screen. Can you see my screen here?
You're good.
Okay, sounds good. So again, thank you everyone for joining. Today, Akash and I will be talking about our project, which is on real-time risk prediction at signalized intersection. We will be using and showing that how graph neural network can be used to model intersections and how safety can be modeled as well through that formulation. So, as many of you know that the intersection crashes, that has been like a constant growing factor of concern for us. And each year, roughly 1/4 of the traffic fatalities, it happens, and almost 1/2 of all the traffic injuries that in the United States that are at or near the intersections. Overall, the number of fatality over the last few years, if you have seen that it has grown, unfortunately. So it's probably time, and probably more emphasis needs to be put into this kind of research. Another aspect is like the rising vulnerable road user death tolls. That number is also increasing, unfortunately. So that's where we at VTTI try to understand that how these kind of problems can be addressed, and mainly through technology, how we can address this one, as well as talk to different practitioners so that we can solve this problem and mitigate these problems and bring some kind of countermeasures. Now, one aspect of this is like nowadays technology has advanced quite a lot. And with this advancement, we can see that particularly sensing, different new sensing technologies are coming. Artificial intelligence is definitely there, but and also the sensors themselves are bringing in artificial intelligence inside them. So the sensor data that we get, sometimes most of the times, like cameras, lidars, and other sensors which can look at the flow of traffic. It can identify that which traffic participants are there, identify the structure of the roadway or the intersection in our specific cases. So that sensing is currently helping us. Now, with that sensing, our main goal, for if we just simply try to say that the major three steps that we want to take is from the sensing, we want to measure some kind of safety metrics. Safety metrics, will introduce some of the safety metrics here, but means with the advent of automated vehicles, we are seeing more and more safety metrics coming, which are pertinent and which are very relevant to overall safety and defining safety of this system. In terms of the safety metrics, once we find out those safety metrics, then the next step is finding out countermeasures. And these countermeasures could be as simple as that if there is one intersection, we are finding that there are lots of overspeeding case, we can deploy some kind of law enforcement. Or if there are some other infrastructure changes that needs to be done for maybe pedestrian safety or maybe bicycle safety, that kind of countermeasures can be applied following these sensing and safety metrics analysis. Now, traditionally, what we have seen is that intersection safety work and methods and countermeasures, this all has been solely and is very heavily dependent on police accident reports and other reports that are coming from like human sources. While these reports are very valuable and means they have shown their potentials, and there has been many countermeasures that has been taken by Federal Highway and other DOTs, which comes from this kind of reports. However, most of these systems are after event diagnosis, and means they depend on human feedback, and the post hoc analysis might also lose the information about that how this crash was caused. So that crash causation was often lost and or maybe partially lost through these reports. So that's where knowing this information more and means trying to understand how we can encode the continuous information for the traffic is very important. And also the crash, beyond crash report, we often talk about the near crash cases, which are more important because that gives us an idea about any particular safety of any particular intersections. As we are growing with the amount of traffic is growing, one intersection which is not historically crash report are very less in certain intersection, it may be that in future those situations may change. So that's where looking at the trend and looking at the temporal trend over months and years of data is very important for us. Now, the continuous assessment of assessment needs artificial intelligence, because a human cannot process all this data simultaneously. We need lots of human hours for that. So that's where artificial intelligence, particularly in last 10 years, have seen very highly promises it has shown in last 10 years. And sensor processing is one part of it, but how to integrate those sensors in intelligent way is another way of another part of artificial intelligence which helps us. Now, if we think about the continuous assessment, it can bring a lot of benefit to our safety pipeline. So first of all is that it can provide some sensing for the vulnerable road users. And there has been many work which basically tries to understand that when the user is present, what kind of users are present, and that kind of more analytical approach towards the vulnerable road user can help us. Next thing is that the situational awareness. If in any particular situation, we need some situational awareness for any event or maybe the traffic volume, the changing traffic volume. If there is some emergency response is needed, that kind of aspect can be easily introduced through continuous measurements. Traffic demand and traffic flow analysis, traffic rerouting, these are also some of the very highly coveted tasks that often most of the DOTs spend time on. And means their research portfolio often includes this kind of traffic flow management. So if we know that a priori that what kind of traffic is going to happen, and say that there is certain event, say a game is there or maybe a concert is there, what kind of traffic that we have historically seen and what kind of countermeasures we can take from there. So continuous measurement and assessment will help us to get into that kind of ideas. Now, intersection in this work, we have specifically looked at the intersections. And intersection is a complex infrastructure. It has, like, as you can see, that this is a four-way intersection, but it has many lanes, and the lanes, they interact in the small area. Even if there is a either for signalized intersection, we have traffic signs, or if we have like non-signal intersections, we have stop signs and other infrastructure-based systems. But still, means they often need to stop at that intersection and maybe yield to other vehicles, yield to pedestrians. And many cases, like if we have like a 3 or 4 lane roads where the rightmost lane is a say that a right turn and the leftmost lane is a left turn, oftentimes we have seen that the lane change happens very close to the intersection as well. That can bring some kind of safety concerns, and when safety, it can have safety aspect of that. Historically, we have seen that the left turn, right turn cases, they often have between 15 to 20% of the crashes. They are pertinent for that. Unprotected left turn is one concern and is an active field of research as well. And for many of the cases, the left turn as well as for the right turn cases, the pedestrian crossing and the bicyclist yielding to them and proper yielding mechanism, visibility, these are current topics of discussion. Now, for the current scope of the project, we mainly try to see that if we can use something which are already installed. In terms of sensors, currently many companies and many solution providers nowadays provide cameras, lidars, and other sensors for that. But that system is very much spurious. It's not very widely deployed. But one thing is very widely deployed, that is our intersection cameras. And it depends from state to state, but this is the map of Virginia. And as you can see, that means there are lots of cameras that monitor the traffic. Can we leverage those cameras? The next thing is that once we get some information about the camera, and we can think about that, means there are like some bicyclists, there are some vehicles, and means they have certain kind of interactions, and those interactions depends on their relative locations. It depends on their relative kinematics as well. Now, how we can connect these dots? And if we think about these three different systems, what should be a proper way of interaction, and what will be a proper way of aggregation of that information, so that we can come back and analyze the safety? And that's where the graph can help a lot. We will introduce that how graph will be helpful for our particular situation. The next thing is that can we study the relative safety of each participant? So, for example, that for vulnerable road users, we know that means the safety, they are more vulnerable for any of the actions, or maybe if any kind of anomaly happens in the roadway, they might be more and more vulnerable. So, what is the relative safety of each of the participants? Can we model that? The last thing is that the graph-based representation of traffic scenes and safety analysis is a new topic. And that topic, given that recent renewed interest in graph and graph neural network, we have seen that we have demonstrated in this project that the graph-based representation can help us get to the goals that we discussed earlier. Now, let me start with giving a little bit of example and schematics through that, how we can model traffic as a graph. So if we have three-lane system, and in those 3 lanes, we have 5 vehicles, each vehicle can be modeled as a node. So a graph is generally a combination of node and edges. Now, each node can be the vehicle, and each node can have their properties as well. So for example, their position, their absolute position, maybe they have speed, they have acceleration. This information we can encode as a node features. At the other point, we can have the edge features. Edge features actually defines that how the interaction between the each two objects are taking place. And it can be their relative distance, it can be their relative velocity, speed, their lateral and acceleration behavior. Everything can be encoded in this particular scenario. And once there is a stable flow, the stable flow will probably have some stable values for all these features. But if there are unstable flow, and say that a vehicle is trying to do a particular maneuver, in those cases, these edge features will be changing, and that encoding will help us to model the system. Now, how to model the system? The idea is that if we can create like a 5-node, and say in this case we have 4 edges, that information can be encoded and aggregated through a graph neural network. And what is the benefit of graph neural network? It can actually identify in 3 different hierarchical levels. One is that it can discuss about the node level. And for example, that whether there is certain anomaly in the node level for that particular vehicle or that particular object. It can also talk about a little bit of the interaction, which is the edge level classification and regression it can do. The edge level information will provide us with more information about the interaction. If there are a potential crash, if there is a potential near crash for this, if someone is exceeding a certain threshold of safety metrics. And at the end of it, we can also look at this holistic view of this graph. So assume that this is a road segment. If we have a road segment like this, then this road segment actually can be classified as risky, non-risky, stable, unstable. It depends on the design of the researcher here. But as we can see that if we start using traffic and model that as graph, we can clearly start to see more features from there. Now, few challenges are there if we try to do this graph-based formulation. One thing is that we need to have a system which is more generalized. If you look at any of this system like this, it can have multiple actors. We need to understand that what kind of maneuvers are possible, what kind of trajectories are possible, and what kind of how we can encode the road information inside that. So for example, that if we have some exit and exit path as well, exit and entry path as well, but at the same time, like there may be other cases where there are like direction of the flow of traffic, how we can encode that. And we cannot try to create separate system for separate intersections. We need to have a generalized solution for that. So that's one challenge for us. The second challenge is that the crashes can often happen to a little bit distant from the actual intersections, but oftentimes that the flow of that intersection or between 2 intersections, if the crash happens, what are the role of those 2 intersections? Can we encode that kind of information as well? The third thing is that how to model these different intersections and maneuvers in a single setting of graphs. So in this work, we will mainly talk about number 1 and number 3. We will give a little bit of highlight about how to code the number 2, but means number 1 and 3 we will mainly talk about. Now, before we go into our actual workflow, let's talk a little bit about the power of graph and power of graph neural network. In last 10 years, we have seen that deep neural network has particularly revolutionized the way that we think about our systems. And deep neural network has like multiple applications. One of them is definitely object detection for that. But how we can use that object detection and scene understanding through computer visions, but then create from a very simple network, road network, we can try to understand the relation between each of the actors. And this kind of relation, we previously talked about their speed and some of the kinematic measures. But at the same time, we can also talk about that where their positional information, if someone is in the middle lane, left lane versus right lane, whether that matters in the overall graph structure. Whether the graph structure, it also says that whether this is on the right side of the vehicle or it's in the on the left side of the vehicle. So that kind of information it can produce. Also, there has been previous work which actually says that we can, from a quantifying variable, maybe a distance, we can also maybe some categorical variable we can use, for example, very near, far, and this kind of variables. And we can clearly see that the effect of this kind of variables. Because if we try to see that if a vehicle is far enough, then maybe those two vehicles will not have enough influence on safety compared to two vehicles which are very close to each other. So this kind of encoding the structural complexity is very important. And also we can see that just the graph, if we just create the graph from traditional graph theory, that structural complexity can also be understood. For example, in this case, we can say that this is a system which has only 3 nodes. And that 3 nodes compared to a system which has 50 nodes has a different implications on safety and mobility. So graph neural network has few other benefits, which are like, it kind of says that what kind of information flows from between the vehicles, how the information propagates over time. Also, the one good thing about the graph neural network is that if we train the system on a certain set of examples, it can be easily transferred. That same learning can be easily transferred to other settings as well. And it often doesn't even depend on the exact structure of the graph that we are creating. So that particular feature is very important. And given that our infrastructure can vary quite a lot, and the number of vehicles can vary as well, number of lane, number of vehicles, everything is part of the variability. We can use this kind of transferability to our favor. So that's why the graph and graph neural networks are really helpful. We find really helpful for modeling this kind of systems. Now, this is one example of the graph representation of intersections. For example, that if we find out that this is a 4-way system, and in this one there are lots of cases where there are like left turns, and there are scopes of like conflict here. In all, this system can be modeled as a graph. Now, let me explain a little bit on the graph here. So the first thing is that the graph are actually like all the vehicles can be modeled as nodes, and all the edges have like a certain kind of relations. And the edges, the direction of the edges, we will discuss in the next section. Direction of and the color we can discuss in the next section. But we can see that means just this whole intersection can be modeled through this kind of graph. And this graph can be dynamic depending on that the number of actors that comes in. This graph can be dynamic, and there are ways to encode this kind of system. But just a takeaway from everything that we said until this point is that the graph representation can be used to just change the domain from the road network to a graph network. So next, we will talk a little bit about the workflow of the process. The way we have seen is that the traffic camera, it can have this kind of views, which actually involves the information about the vehicles or maybe other actors it has, their relative positions between each other, and also their lane information and relation to the infrastructure as well. What we can do is that we have used this and the Google Earth view to understand, that means in terms of GPS coordinate, if we want to convert everything to the bird's eye view, and means there are certain benefits that Akash will discuss. We can convert the system there. The next part is that once we can do object detection, and all these bounding boxes are actually talking about the object detections here. So we can look at object detections and then track them over time to find out that what are their trajectory. So we did that. At the same time, we can classify that whether someone is VRU or versus someone is a vehicle, their classes as well. The next thing is that we can use something called lanelet road mapping, which actually converts the overall road structure into small segments. And those small segments can be used as node again for a graph. Once we do that, we can find out the kinematics of the system. We can add this lane information and then create something called a semantic scene graph. Then we can add the other information, which is from our traditional safety knowledge that we have, and it can be simply their overspeeding, or it can be like post-encroachment time on TTC. This kind of information we can put in and do a graph neural network-based training and try to predict some kind of risk score from there. Now, for like traffic object detection and tracking, we need to do like multi-object tracking simultaneously. And in last 7 or 8 years, multi-object tracking has really been promising. It is almost real-time processing we can perform. So this was from one of our previous safety report, safety project, where we try to understand that how, given that the low quality of the images, we can still properly detect and track each of the vehicle and their trajectory and convert them into road networks. The next work, that once we have the object detected, we know their locations in the image plane. It is important to convert from the image plane to the GPS coordinates. We use the Google map to convert the GPS coordinate and find out a homography matching between the images and the GPS coordinate. This needs to be done for every single intersections, because means every single intersection may have different structure, and that structure needs to be properly encoded from one to another. The next thing is that the lanelet. So lanelet is a small segment of road which are generally homogeneous in nature. And when we say homogeneous in nature, it can be that their roadway structure, it can be roadway curvature, it can be their speed limit. This information are very much consistent. Now, for lanelet, we need to have information from the from something like OpenStreetMap, or any of the map encoding is needed in there. So the map encoding directly goes into the into this information, and then we can find out, divide the system into small segments. So all the dots and segments that you can see, they are actually a small lanelets. And when we will be next talking about semantic modeling, we will see that means why this is important for us. The last one is that the projection of the system into Frenet space. Now that we know that each road segment, how their structure is and how their curvature, road curvature is, we want to think about that how actually, rather than from a clear Cartesian coordinate, if the road has a curvature, how we can model the distance and other kinematics. And Frenet space, if we convert the Cartesian space to the Frenet space, that actually helps us to project this. So now that we know that what is our overall pipeline, now we will talk a little bit about the traffic scene graph. And the traffic scene graph in this project, we have mainly looked at 2 different ways. One is that the elementary traffic model, and the second is the semantic scene graph. When we talk about the elementary traffic model, we are talking about mainly that how the graph looks like. And the graph theory actually has a lot of information itself that we can leverage from just looking at the graph. Even if we don't know their relation, we can still understand the graph. So generally, the way we have encoded here is that if two variables, or means two objects, has a distance less than a certain values, in this case, we have taken 10-meter values. If they are, then there is an edge exists there. If not, then that edge doesn't exist. Now, using that, we can convert any traffic at any point of time to a graph, and then use simple information from their the overall vertex. For example, that we can understand the node. We just from the number of node, we can understand the degree of a particular node that they are connected to. So this kind of information can provide us maybe information about traffic density, information about how many intersections, how they have to negotiate the system all the time. So with that, I want to transfer to Akash.
Thank you, Dr. Abhijit. Yes. So far we discussed like what is elementary traffic model, where we just create a graph based on the distance metric. That is, if two nodes or two traffic participants are less than a defined distance, then we create an edge. But this kind of a graph creation method does not take into account the road structure, or how the intersection is structured, how are the different lanes related to each other. So what we use is something called as a semantic scene graph. So a scene graph is a data structure commonly used in computer graphics to represent a hierarchical tree-like structure of objects. So scene graphs are different from normal graphs in that they're not just a collection of nodes and edges, but they have a parent-child relationship. Additionally, each node in a scene graph typically stores information about its position, appearance, and behavior in the scene. So a semantic scene graph, in addition, represents a scene graph in terms of its semantic meaning. That is, each node represents an object in the scene and is labeled with a category or a class. And this can be things such as whether the traffic participant is a car, whether they are a truck, whether it is a pedestrian. So this kind of information. But additionally, the semantic scene graph also captures information about the functional and semantic relationships between the objects. That is, it may indicate that a pedestrian is located next to a vehicle because the vehicle is in the rightmost lane, something like that. Or it may be that two vehicles are related by a longitudinal relationship. It means that one car is in front of another. So this kind of information helps us take into road structure into account, and gives us a much more meaningful definition of a graph. Can you go to the next slide? Yes. So here we look at an example intersection where from Blacksburg, Virginia, and we'll first create a road graph for this intersection. The next slide. So yeah, so here we use the lanelet. Here we use to create a map in the OpenStreetMap format. So here, each section of the road segment has been labeled with a different alphabet. So here there are 6 road segments, as you can see, and each road segment extends a few 10 meters, and each road segment represents a uniform section of the road. So the colors, there are 2 different colors, if you can see. The green color indicates a boundary between a road and a non-road surface, whereas the blue lines indicate a boundary between a road and a road surface. So here there are 6 road segments and thus 6 lanelets, and we create a road graph based on this road intersection in the next slide. So yeah, so here we can see the same representation which we saw in the previous image, but we have eliminated the background image from Google Maps. So as we can see, there are 6 road segments and we have a road graph on the right. So the road graph encodes information about how these road segments are related. So for example, B and F, these road segments are located one after the other in the road structure. But not just that, if you take into account the direction of the flow of traffic, we see that the traffic flows from F to B because it's a one-way road. So we have a longitudinal red edge, if you can see, which goes from F to B. Similarly, we have a red colored directed edge which goes from E to A, which indicates that there is a longitudinal relationship between these two road segments. That is, traffic flows from E to A in a longitudinal manner. That is, these two road segments are connected one behind the other. There's also another relationship which we call as lateral, which means that these two lanes or these two road segments are adjacent to each other. So for example, A and B have a lateral relationship, and this is a bidirectional relationship because there is no defined direction that vehicles will only go from A to B and they won't go from B to A. So vehicles can go from either A to B or B to A. So therefore, we have a bidirectional relationship. Similarly, for E and F, we have a bidirectional lateral edge. And finally, like the third type of edge we have here is the intersecting relationship, which is road segment C is intersecting road segment A, and road segment D is intersecting road segment E. So these kind of three different types of definitions of edges helps us to understand how road segments are related to each other. And once we are able to describe how the road is structured, we can take into account the location or the coordinates of the vehicles or the different traffic participants and understand how they are related to each other. So going to the next slide. Here we show an example scenario in the same structure, in the same road structure, which we saw in the previous slide. And here we have three vehicles, vehicle 1, 2, and 3. Vehicle 2, for each vehicle, we project them onto the center line of the lanelets, and this is done so as to take into account the Frenet coordinates, which allows us to compute distance along the center line or along the road curvature and not the Euclidean distance. So vehicle 1 has a single projection and vehicle 3 also has a single projection. And this is just for easier understanding, but vehicle 2 has two different projections, one in road segment E and one in road segment F. And although we have multiple projections for vehicle 2 in this scene, but when we create a semantic scene graph, finally, we combine all this information into a single node, and this is to avoid having multiple nodes representing the same traffic participants. So this traffic scenario, so in this traffic scenario, we saw how three vehicles can be projected and onto the corresponding lanelets. And if we go to the next slide, we can create a semantic scene graph. So for semantic scene graph, we consider the locations of these vehicles in the original road structure. So we have vehicle 1, 2, and 3. Vehicle 1 is located in road segment B. Vehicle 2 has two projections, one in road segment E and one in road segment F. And 3 has a single projection, which is in road segment C. So if we want to know how if we want to know how 1 and 2 are related, particularly we want to know how the projection of 2 in F and projection of 1 in B are related, we go back to the road graph and we see that B and F are related longitudinally. That is, an edge goes from F to B. So therefore, we create a longitudinal edge going from 2 to 1. And the red color and the direction indicates the direction of flow, and the red color indicates that it's a longitudinal edge. Similarly, if we look at the projection of vehicle 2 in road segment E and see how it is related to vehicle 1, which has a projection in B, we see that if we look at the road graph and we see how E and B are related to each other, we see that there is it's not a direct path, but we have to go through a bidirectional lateral edge and then through a longitudinal edge to go from E to B, which is we first go from E to F and then we go from F to B. And therefore, we are able to create a lateral edge between 2 and 1. And the direction indicates how we move in the graph when we go from E to B. And finally, when we look at traffic participant C and traffic participant 1, 3 in road segment C and traffic participant 1 in road segment B, and we look at the graph. So there's a bidirectional edge which goes from C to A and another bidirectional edge which goes from A to B. and we are thus able to create an intersecting relationship between vehicle 1 and 3. And similarly, if you look at 3 and 2, particularly if you look at the projection of 2 in E and projection of 3 in C, and if we look at the road graph again, and if we see how we are able to move from E to C, we can go from E to A in a longitudinal manner and from A to C in an intersecting manner. And thus we are able to create an intersecting relationship which goes from 3 to 2. So this kind of a definition of creating a semantic scene graph allows us to take into account the road structure and create a semantic relationship. Also, one more thing which has to be taken into account is, in practice, it also makes sense to limit the length of the path. So when we go from different road segments, such as from C to A to B, and like so on, we have to limit the length of the path, because it's not true that two traffic participants which are located like several hundred meters apart, they would be related. That's not true. So we usually restrict this length of the path to something like 30 meters, so that we don't have edges between traffic participants that are very far away from each other. Coming to the next slide. So yeah, so we use something called as graph neural networks for forecasting or making any predictions regarding the traffic safety, which we'll explain in the further slides. So graph neural networks allow us to aggregate information from neighboring nodes. So if you look at the example here, and we look at node A, so in every layer of the graph neural network, we're able to aggregate information from the neighboring nodes. So after one layer of the neural network, we are able to aggregate information from nodes C, B, and E. And if we go a layer deeper, we are able to aggregate nodes from node C from the nodes B and A, and so on. So the number of layers in the graph neural network allows us to understand how far in the network are we able to aggregate information from. So features of nodes and edges in the one-hop neighborhood of the target node are considered in every layer of the neural network. And this operation is also called as convolution. And there are different variants of graph neural networks, such as convolutional neural network, attention-based neural networks, and so on. And they all mainly differ in the update and aggregate step. So update step, in the update step, we are able to combine, can you go one slide behind? Yes. So in the update step, we are able to combine information from nodes C, B, and E in the case of A, and we are able to aggregate it with different functions. This can be functions such as mean, maximum, average, or use a neural network to create an embedding for the aggregation. Can you go to the next slide? So now we look into how graph neural networks can be used for safety analysis. And one safety metric which is very easy to estimate is the speed and acceleration. And here, because we look at signalized, in general, overspeeding and underspeeding, like driving too slow, are both considered very dangerous because they both affect the flow of traffic to a great extent. So therefore, we threshold the speed limit at vehicles going more than 10 miles per hour, which we consider as overspeeding. But because this is a signalized intersection, we do not consider vehicles moving slower than the speed limit for this case. But for sections such as the highways or interstates, we would consider underspeeding participants as well. And rapid acceleration and sudden braking are also considered for this case, for this situation. And we restrict these values to 0.6 G and 0.5 G based on the safe values for accelerating and braking for vehicles. Can you go to the next slide? I think skip a slide in between. Yes, so we calculate different safety metrics based on the kinematics. Two of the most common metrics are TTC and post encroachment time. So TTC is defined as if two vehicles are moving longitudinally in the same or opposite direction, the time they would take to collide if they continue their trajectories. And here we threshold this value at 2 seconds. But because this is a signalized intersection, we combine the TTC with speed and acceleration to discard multiple false violations. Post-encroachment time is a crucial metric which is used to assess the risk of collisions in traffic scenarios. It represents a time interval between one traffic participant leaving an encroached region and another participant entering the same space thereafter. And post-encroachment time directly measures the amount of time available for road users to react to potential hazards, making it a valuable indicator of collision probability. So to evaluate PET values, this study focuses on pairs of participants that exhibit either a lateral or intersecting relationship as determined by the semantic scene graph. So intersecting relationships commonly occur at traffic intersections or when one road merges into another. And lateral relationships, on the other hand, are when two participants occupy adjacent lanes and may potentially cross paths if one or both participants decide to change lanes. So unlike the TTC or speed and acceleration, PET, which is the post-encroachment time, it cannot be obtained through a straightforward formula, and it requires the identification of instances where a current participant intersects with a point previously traversed by another participant. And this calculation considers the requirement that two participants share a lateral or intersecting relationship. And because it cannot be computed mathematically, because we have to look at the trajectory history and see if they are crossing paths at any point, which is why we use the neural network based approach for estimating PET values. And in this study, we threshold this value to 1.5 seconds. Next slide.
All right, Akash, we just need to finish the whole webinar up in about 5 minutes.
Okay.
So Akash, maybe we can go to the result and experiment section for now, and I think that the slides will be shared with everyone. So maybe in a few minutes we can wrap this up.
Yeah. So in this work, we look at two particular intersections. One which had statistically relatively higher number of crashes, and the other with a relatively lower number of crashes than the rest of the areas in Virginia where the camera feed is available. Also, these intersections had relatively less noisy video feed, and most of the videos in this data set are 320 cross 240 RGB videos at 15 frames per second. Next slide. And this is something which node level features are these, like we compute these based on the structure of the graph. That is, we don't take into account the kinematics, but based on the graph structure, which you can see in this image, we are able to provide information regarding the structure and position of the nodes in the network. And it also allows us to understand how important individual traffic participants are. Also identify if there is any patterns in the network's overall structure. So one metric is degree, which you can see in the graph in the table. So degree refers to the number of nodes connected to a given node directly. And based on the data in the table, it is evident that cars, trucks, and motorcyclists typically have an average degree of approximately 2.5. But on the other hand, bicyclists have a higher degree because they share edges with both pedestrians and vehicles. However, due to the narrower cycling lanes, there tend to be more traffic participants within a distance radius which we consider to create the graph. And consequently, cyclists are generally at a higher risk as they have a greater number of traffic participants in close proximity. And moreover, among all the road users, cyclists experience the least amount of safety. And this is primarily due to their higher exposure to nearby traffic participants. So eigenvector centrality measures the traffic participant significance with the network. And based on the table, it's evident that pedestrians hold the lowest influence on the network, while others hold relatively comparable levels. And between centrality quantifies the extent to which a traffic participant facilitates connections. And coming to the link level features, if you can go to the next slide. Yes. So this provides us information about how individual edges or links can be used to understand the relationships between nodes. Local neighborhood overlap, it measures the similarity between the sets of neighbors of two nodes in a network. And there are two common local neighborhood overlap metrics, which is Jaccard index and Atomic Adar index. So Jaccard's coefficient measures the similarity between two sets of data, and it is defined as the ratio of the number of common neighbors of two nodes to the total number of neighbors of the two nodes combined. Whereas Atomic Adar index is based on the idea that the importance of a shared neighbor between two nodes is inversely proportional to the number of neighbors that the shared neighbor has in the network. Then go to the next slide. So this is the coming back to the flowchart. So this is a flowchart which we saw initially, and and based on this flowchart, we'll be looking into the graph neural network training part, based on the graph structure which we created so far. If you can go to the next slide. So we use two different types of neural networks. One of them is a graph convolution network, which takes into consideration neighboring nodes and edges and aggregates information. But there's another neural network which is called graph attention network, which not only aggregates information from neighboring nodes and edges, but also applies specific weights. And this is based on graph attention networks use something called as self-attention. So these weights are computed based on the nodes and edge features themselves. So they are able to understand which traffic participants in the neighborhood are more relevant to focus on. So which, suppose there is a participant who is speeding a lot, or someone who is braking suddenly. So this kind of information can help weigh the importance in a different manner and allow us to combine this information to the neighboring nodes or neighboring edges. And coming to the next slide, which shows the results for these two neural network based approaches. And we see that with graph attention neural networks, we're able to obtain an accuracy of 72.9%. And with that of convolutional networks, we're able to obtain 79.85% accuracy. So with that, I'll pass it back to Dr. Abhijit.
Oh, hi. Thank you, Akash. So just quickly wrapping up, that means what is our key takeaways from this is that the one big takeaway is that we can encode the infrastructure, the road network, and the vehicle network together in one composite network, and then analyze them through graph neural network. The code will be available in this link. The one thing that we want to discuss for like the practical limitations that we realize is that the current camera infrastructure doesn't give us a very high resolution images, and what that translates to is that means there are more elements of errors in there. So if the infrastructure gets upgraded, then this kind of information can be more and more included in the system. The other system is that we don't have adequate annotation for safety events yet, because means this needs, like the safety events when we are talking about, it's not only crashes but also near crash cases. We need more and more annotations for that. And the other thing is that the camera, it has a certain field of view. It cannot provide a very high field of view for the 360-degree view for that. So that's another limitations that we had to think about. So just in order to address that, we are starting a new data set. So we have connected with total of 4 intersections in Virginia. And also we are collaborating with Tsinghua University from China. So that means it can be a more diverse data set for us. So future scope is definitely, we are still continuing this work, and means hopefully we will have a workshop in IEEE IV following this work, and also we are working on a large scale data set as well. I want to thank MyVision and Oracle Cloud for supporting this. We used Oracle Cloud for processing the data, and MyVision gave us some key suggestions about this. And also safety is definitely for funding this project. If you have any question, please send us an email. Thank you, and I'll be happy to answer questions, and I'm happy to stay longer if needed.
Thank you so much, both of you, Abhijit and Akash. I do have one question. Can this work be expanded to multiple intersections?
It can actually. So means one thing is that means if we think about this as the 2 or 3 different intersections we have, and for each of the intersections we can model this kind of graph, and now those graphs actually becomes embedded into a larger graph, which can be now think about that, okay, one node becomes like one graph, and one intersection becomes giving information, one node is giving information from one intersection, and another node is giving information from another intersection. I mean, this kind of work has been done a little bit part of Google Map as well, where like this kind of different intersections and different roadways are connected in that way.
Thank you. You're muted, Laurel.
Thanks, Aram. I just wanted to first thank everybody for attending. You can still continue to send questions via the chat or the question and answer section. We do have the whole recording recorded, or sorry, the whole webinar recorded, and that will be sent to you when it's available. It will be on YouTube, as well as the slides. The presentation will also be available. So you will get an email regarding that shortly. It's usually within a week. So, and then I just want to let you know that in the chat box right now, I am sending a link to the next webinar, which is going to be on connected vehicle data safety applications, and it's going to be presented by researchers from Texas A&M Transportation Institute. That project evaluated the viability of connected vehicle data in roadway safety applications with the objective of improving existing predictive crash methods. So that webinar is actually scheduled for November 15th at 3 o'clock Eastern Standard Time, and you can register via the link that is been provided in the chat. All right, Aram, has there been any more questions?
We just had a question about the recording being made available, and as you said, it's going to be posted to our YouTube channel.
Okay. Actually, we do have a question coming in. It says, Abhijit, how the train and test data sets were split, if you could explain that.
Akash, you want to take that?
Yeah, sure. So we choose two different sets of intersections for training and testing. And for one set of intersections, we have multiple videos. So we use all those videos from those sets of intersections for training and a different set of intersections for testing, so that we are able to make the model more robust and able to learn information which is not specific to an intersection. So we are actually able to generalize better, because we're able to we are using information from different intersections, and we're applying them to a different set of intersections. So in the end, we are able to make the model make the model more generalizable. So that's what we do. That's our split.
All right. Well, oh, we have another one. What deep learning model was used to detect the road users?
So we used multiple models, but means for the final results that we find out that bot sort was a good model to use, but also we used our own GCNN match, which is also specially trained for object detector and multi-object tracking in like this kind of data sets, which are like low resolution data set.
All right. Well, I'm going to officially thank everyone now, and thank you for attending. But Abhijit did say he can answer a few more questions, so please hang around if you would like to. Otherwise, again, thank you very much. We hope to see you next month. Abhijit, you had another question, which is, person asked, can I know the accuracy of the detection?
Accuracy of the detection. I think that you can look at two places. Number one is that we have an IEEE ITSC paper where we showed that accuracy, and also for the bot sort, you can look at the bot sort paper for that. Also, for the GCNN match, we were at one point of time we were in the top 5 of the MOT challenge as well. So maybe you can go to the MOT challenge page as well, and means there you can see the accuracy that we have reported. But everything is consolidated in our IEEE ITSC paper, and we also have a manuscript archive paper. Maybe I can try to send this to.
Yep, and I was actually going to say also, for those of you interested, when I do send out the link for everything for the webinar, as well as for the slides, I will also be sending out the link to the project site. I'm going to send that out to everyone again right now. And this project site is also going to house all the papers and links that have been created from this project as well. So you can always look there for those things. But again, it will come in an email to all those who attended today or registered today.
So Laurel, I should paste in the webinar chat this one.
Yep, you can go ahead and paste it in.
Okay. So this is
Thank
one
you very
paper,
much.
and also the other one is, I will just post this one as well. So in this too, you can find out the information about the accuracy, particularly on this kind of data. And we had some other algorithms as well.
All right. All right. Well, thank you very much, Abhijit and Akash, for presenting the information today and for doing all the work you did with safety.
Yeah, thank you for organizing.